Hello everyone. In the previous podcast number 6, I discussed the basic definitions of the terms we use in the Lean Six Sigma acceptance process. In order to solve such model, I mean determine its parameters statistically, we need an appropriate computational methodology. In our case, it will be the so-called structural equation modeling, SEM. Let me say a couple of words about SEM. Structural equation modeling is a second-generation multivariate analysis method in which directly unobservable latent variables, also referred to as hidden variables, constructs, or unobservable factors can be used, which makes it an interesting tool for solving research problems. In essence, SEM is an extension of the general linear model, which allows a researcher to analyze a set of regression equations simultaneously. All belts basically should remember general linear model from Minitab at least. The SEM technique is particularly useful in non-experimental research in which hypothetical structures, usually referred to as models, can be subjected to tests to indicate the extent to which they are supported by a dataset. SEM is mainly a method for confirming models rather than exploring them. This means that it is more often used to determine an a priori formulated model of a substantive process, psychological or sociological, than to find an appropriate model for a given set of empirical data. The model contains elements of theoretical knowledge representation and generalization of previous empirical research results. It should be emphasized that the use of such statistical model somehow forces the researcher to determine the causal mechanism that underlies the observed correlations between variables. Simply saying, guys, any model without the theory applied, the theory behind the model, doesn't mean anything. I don't speak about theories applied here. You can go to books which describe this area. Consequently, SEM is today one of the most important data analysis strategies in the social sciences, including management, of course. Generally, in a structural model, variables are divided into exogenous and endogenous ones. Exogenous variables, I'm showing now, are variables whose causes are not included in the model. Endogenous variables are those whose causes are included in the model. They will have paths in the form of arrows, which the heads pointing towards each other. The determinants of exogenous variables, let me call them external factors, are outside the considered model. So these guys are outside the model, the SEM model, and we call them, okay, external factors, but they are working together as a a kind of measurement system for the applied SEM model. Okay, so this is the role of the external factors because they are measurable. The model shown is a path model where the paths represent dependencies between variables, and they are, as I said, represented by arrows. The direction of the arrow is from the causal variable to its effect. Observable variables are usually represented as a square or a rectangle, and latent variables as circle or oval. Indicators are often placed next to the arrows to indicate the direct impact of the input variables on the output variable. A path graph is also a graphical representation of a system of equations. The main task of SEM analysis is to estimate model parameters and assess the model's compliance with the data sample. In statistics, we call this, of course, as a goodness of fit. The model presented is already adequate and fitting the data. The process of estimating SEM model parameters is an iterative process whose algorithm for finding the minimum value of the fit function is included in many modern statistical packages. As you have noticed, I used one of them, which is equipped with the SEM methodology to calculate the estimates of the model. Here I'm using the so-called ML estimator. Let me find this parameter setting, analysis properties. So if we go to estimation tag, you can see maximum likelihood. So this is the ML estimator function. It is the most frequently used and basic estimator in SEM methods, especially for those which are based on the covariance matrix, something we call covariance-based SEM. To relax the assumption of normality of multivariate distribution, we are dealing here with multivariate distribution, the ML parameter estimation method with bootstrap sampling was used. So you can find another tag called bootstrap, and the perform bootstrap is here checked, as you can see. In a nutshell, bootstrap involves sampling from a set of data obtained during a survey and is based on Monte Carlo simulations. Okay. What we mean here is to artificially increase the sample size for estimating model parameters using SEM. You can guess why this is so important. I have already talked about it a bit. The presented SEM model is graphically represented using a path model where the cause and effect relationship is symbolized by an arrow pointing from the independent variable to the dependent variable in a given relationship. Each arrow corresponds to one path factor. The path coefficients here are the regression coefficients. I will calculate soon the regression coefficients and I will show you them. Random components, including residuals, are represented in circles with the description E. Of course, every variable estimate has a residual. This is obvious. Okay, so let me run the simulation, the calculations. So we go to the menu, Analyze, and Calculate Estimates. You can see here the simulation was running and it is already finished. Where are the parameters calculated? We have to go to View and open the text output. We don't have time to review all the information presented by the program, by the software, but the estimates of the variables you can find here. You have to click on that and you can see there are calculated regression weights, standardized regression weights, covariances, correlations, variances, very important. You can see the estimate of each parameter. You can see the standardized error, of course, and the p-value, which allows to make a decision what is significant, what is not. Okay, there is a lot of different information. I have described how to deal with this output in my book, so I kindly invite you really to deepen your knowledge about it, to understand how the statistics works. Okay, so what I have found in general in this case, just to summarize, in the confirmatory factor analysis we just did of the SEM model, as a tool for verifying the measurement model, it is assumed that the standardized values of path coefficients should exceed the desired value of 0.7. As it can be seen from the data summary in the presented tables, only P3 parameter, this is personal openness to the use of new ideas and practices, does not reach this value. At the same time, the value of 0.663 can be considered acceptable. All values of these loadings are positive, so external factors will strengthen the explained variable and are statistically significant at the significance level alpha of 0.05. Moreover, according to the cited authors, the percentage of explained variance should exceed the desired value of 0.5 for those factors whose loadings exceed 0.7. This condition is met for all factors. Only for P3 again, P3 seems to be is very interesting weakness indeed. For the researched population, which did not reach the loading value of 0.7, the value of the explained variance is 43.9%, which is not a bad value. All correlations here, you see, are positive, which means that there is a positive linear correlation between the variables. In other words, an increase in the value of the explanatory variable will result in an increase in the value of the explained variable. In this model, endogenous and exogenous variables stimulate the process of acceptance for Lean Six Sigma. This is an amazing statement, okay? So what we should do then from practical perspective, we should take actions which increase the values of the parameters, both external and internal to the model, because all of them can stimulate positively the acceptance process. That's an amazing statement. This is why we do, because this is the monitoring and this is the diagnosis. Okay, so going back to the model, I can present the values of the model. Just clicking on that, you can see the regression coefficients and of course values of the parameter estimates. Yeah, so please remember that behind the model there is a theory applied. This is extremely important. There is a cause and result effect between the parameters. So we have internal factors, okay, and external factors, which model beliefs, our beliefs. In this case, it is the first belief is called perceived easy of use. The second one is perceived usefulness. Okay. So these beliefs are our cognitive response. They tell us about us, how we think, how we know the Lean Six Sigma, and this is basically a predictor what we will be doing with that further. So further, these guys are affecting our emotional response. And we call it affective response, because in affective response, the beliefs we have, which can support the acceptance here or stop, create the attitude. And the attitude is our, as I said, affective response. So we are dealing in the next stage of acceptance process with a kind of emotional reaction, because we are all humans, but we are not only rational, we also are emotional, and that is the problem. This is one of the problems, of course. So it's not easy to predict, and it's not easy to measure the acceptance process. So if you tell me, can emotions be turned into calculations? Can emotions be presented as numbers? Can emotions be statistically verified? Yes, my response is yes. It is exactly what I just showed you. These statistics tell us as well about affective response, and this is amazing correlation. As you can see, the process can be very interesting. It's all about humans. It's all about what we do and how we implement the Lean Six Sigma. It's a very great human process behind. This is very interesting. I really encourage you to deepen your knowledge, to read books about it. Okay, so I believe that today I explained the relation between statistics and emotions, and can emotions be really measured and statistically explained? The answer is yes, and this is one of the examples. I believe this simplified approach I used in my podcast because speaking about it in detail could take long hours. Explain you enough that it makes sense. In the next and last podcast of the series, I will show you what to do next with these results, as they will be used to draw up an improvement plan. I a couple of times referred here to the P3 parameter. So we have to, in general, catch all weaknesses we see in the statistics presented, and they will be our area of improvement for further discussions, for working on our improvement plans. Thank you for today. See you next time.